My name is Prakash Gupta, and this is my Physics 2211 Lab 3 video report. Introduction. So first, let's talk about goals. And the goals for this lab were to develop simulations and analyze the resultant data to find experimental values and analyze systems. In instructions, we would begin from two types of starter code and develop simulations which will A, allow you to calculate the mass of a black hole, and B, a simulation that will result in an orbit of a spaceship around a moon and planet. The principles related here are Newton's laws of motions, gravitation, and the update equations, as well as some circular motion. Our results, we found that the black hole had a mass of 6.3 times 10 to the 43 kilograms. That's big. And we found a not necessarily so stable orbit for the spaceship using an initial speed of 25 kilometers per second in both the x and y directions. So let's talk about those major principles again. And again, that's gravity. And we have both of these interactions happening in space, so we'll use the universal law of gravitation, which is given by the equation shown here. Newton's second law, force equals mass times acceleration, the update equations, which are there, and this principle from circular motion that F perpendicular is equal to mv squared over r. So let's talk about the black hole. We would alter the starter code to account for and simulate the forces of gravity acting on a star orbiting this black hole. And then we can solve the gravitation equation, which is our only force happening, for large M, the mass of the black hole. And at each point, we'll have a slightly different approximation. So we'll take many of these approximations and average them to find our estimation. Look at the code here. We walk through finding the initial and final momentum of the star, then the change in velocity and change in momentum. Then we can find our force, which is equal to dp dt, the change in momentum with respect to time. And then we can find the parallel component and the perpendicular component using Newton's second law as well. So we can then find that the mass of the black hole is given by that force. In data analysis, we can plot all of these values, and we find that they are relatively normally distributed and that the mean is the value we discussed previously, with a standard deviation 2 orders of magnitude smaller, which is significant data to suggest that this mean is our actual mass of the black hole. Moving on to the spaceship, we were to develop a similar simulation, this time with 3 bodies, a planet, a moon, and a spaceship where we take the planet to be fixed. We implement the code governing the motion of the other 2 objects and their dynamic gravities, and we're to test values of initial velocities for the spaceship, which will allow it to orbit the other 2 without escaping or crashing. So let's walk through the code really quick. So we first need to calculate the radius between the bodies acting for both the planet and spaceship and for the moon and planet and moon and spaceship. But we do that first by calculating the radiuses so that we can calculate the forces. And we know that there are only 2 forces acting on each object because there are only 3 objects in total. So we have our F net. Then we use the position and update equations, position and velocity update equations to find the actual values of the positions, and we can graph them over time. We can see here that where the cyan is the motion of our planet and the pink is the motion of our spaceship, we are orbiting both bodies and we aren't escaping. So we've completed our goal using the speeds of 25 kilometers per second. Regarding conclusions, that was our conclusion for part 2, and our conclusion for part 1 was 6.3 times 10 to the 43 kilograms for the mass of the black hole. Error may have arisen through rounding, and for the spaceship, it's unknown whether or not the ship would remain in orbit beyond 1,000 hours, which was outside our scope. What does it mean? So how does net force relate to parallel and perpendicular components of rate of change of momentum? And we know that as momentum is given as the product of mass and velocity, and force is given as the product of mass and acceleration, following from the fact that the acceleration is the rate of change of velocity, we find that rate of change of momentum is directly equal to the net force. Regarding parallels and perpendiculars, we know that net force is in the perpendicular direction, impact direction of motion, whereas forces in the parallel direction impact speed. Regarding an imaginary system with a black hole, star, planet, and moon, if we wanted to predict motion of the entire system, we would need to include in our model the interactions of gravity between all of these bodies, as each body would act on each other body. However, the black hole would dominate all of the others because of its mass in several orders of magnitude greater than the other objects. The force of the spaceship on the black hole is entirely negligible because that force will not accelerate the black hole with any great amount. That being said, thank you, and this is the end of my presentation.